Okay, so it's like this up and down. So it's like goes down and up, right? But then each one of these down and ups is a bunch of down and ups, and zooming in on one of those is just more of the same. It's almost like a fractal, if anyone's ever seen a fractal. It's like you zoom in, just keeps on having more and more detail in it. And so that's the function. If you want to know what the actual function is, like what is the f of x? Do y'all want to see it?
Yes.
It's that right there. So it is an infinite series, which we haven't studied series, and that's a Cal 2 topic. This is an infinite series. So it's an infinite summation of cosine functions. Somehow, if you put a bunch of cosine functions together and add them up, and it goes forever, you get the Weierstrass function. And that's just kind of an animation of it developing the function. Starts out with these little undulations, and you have more and more undulations. The more and more of these you add up, the more you get the little discontinuity. So it's like an infinite saw blade. It's a weird function. All right, just wanted to point out. Let's see, 2:41. Do we want to take a break?
Yes.
Yeah, let's do our break. 5 minutes or so, 6 minutes. We'll come back. We're not done with this section. We still got more to do. All right. So before I get into the rest of this section, basically what we've done is we've said if we start with a function, we have this thing called its derivative, and that's a new function that we can graph, right? I think this is a natural question. I wonder if there is a function that when you graph it, it's what? The derivative is the same graph. Like you mentioned, like those look similar, but mathematicians asked for a long time, I wonder if there is a function, question, right? Is there a function that is equivalent to its own derivative? Like when you do this operation of the limit and all that, that you get the original function you started with. That seem like a natural question to ask? Well, there is one that you could think of, I mean, that if I show it to you, I think you would just be convinced pretty quickly. What about f of x equals 0? Graph it. What does it look like? Horizontal line going through 0, right? And then what would its derivative look like? If you go to any point on this graph, what's the slope of the tangent line? 0, which would mean that's the same graph, isn't it? It would just be the same graph. So do you all agree that that's an answer? F of x equals 0. Its derivative would also be 0. Yeah? Okay, this is what we call the trivial solution. This is the trivial answer. Meaning, yeah, but that's a boring function, right? F of x equals 0, what does it do? You feed it anything, it spits out 0. Who cares? It's not a very useful function. So we said, okay, is there another one? Are there an infinite number of them? Are there only a few? Let's go try and see if we can find one. And we went looking, and we found it. We finally found it. Does anyone know what it is? Yes?
E to the power of x.
E to the x. It's what you studied in college algebra. It's that function f of x equals e to the x. And I'm not sure how much your college algebra teacher told you, but the reason why this function is so important to us is because it is the only function, other than this trivial one, it is the only function that satisfies this. That when you graph it, right, you all know what e to the x looks like? Looks like this. Right, that's what e to the x looks like. If you go and try and graph its derivative, you're going to draw the exact same graph. Let's see if we can maybe convince ourselves that that's true. What would the slope of the tangent line be back here? Right here. What would it be? Small, positive, right? And then what's happening? Positive, positive, getting bigger and bigger and bigger? Positive, positive, getting bigger and bigger? Isn't that exactly what that graph does? It's small, positive, getting bigger, bigger, bigger? So I'm not here yet to convince you that this is true. I'm here to just tell you that this is true. So right now you'll just have to take it on faith. I'll prove it to you later that the derivative of this is in fact itself, all right? So that's why that function is so important to us. It's unique, meaning that it's the only one, other than that one, it's the only one that behaves that way. So there's not a real easy way for us to explain why it's e to the x, like why it's not 2 to the x or 4 to the x. It's e to the x. And that's why e is so important, because we can't quite explain why that number works, but that's the number that works. It just naturally occurs that way, which is why we call it the natural exponential function. Natural meaning, yeah, that's just the way the universe is. That function works. All right, Weierstrass, we're moving on. Higher order derivatives. So if we start with a function, right? Like let's say we start with a function and we do this thing called taking the derivative of it. If it spits out a new function, right? This is a new function. Then what's stopping me from doing the same procedure on this new function? Like acting like I never even knew that was there. That's the function I started with, and then doing the derivative again. Wouldn't that spit out a new function? Yes? And then that function, I could act like that's some function, take its derivative again, and I would get a new function. Couldn't I just keep doing that? Those are called higher order derivatives. So we start out with some notation. F prime of x is called the first derivative of a function. That means you've taken the derivative one time and you got a new answer, right? A new function. If you do two little prime marks here, then that's called the second derivative. And what it means is you're taking the derivative of the derivative. So a second time. And then third derivative, you do three prime marks, third derivative. That's the derivative, take derivative again, take derivative again. And then it starts to get a little annoying with the primes, right? Because you start, what about the fourth, right? So what we do is we write f with a parenthesis superscripted up 4. Do not confuse that with this. These are not the same. The one on the left means what? Yeah, take your function and raise it to the 4th power. That means multiply it times itself 4 times. The one on the right means take the derivative 4 times in a row, right? So that's how you can distinguish between the two. The left one is powers, the right one is derivatives. By the way, using this notation, what do you think this means? That would be the 0th derivative. What do you think that means? Just the original function. That means don't take a derivative. That comes in Cal 2. We'll need that in Cal 2. So this just means the original function. And then you have the first derivative, second derivative, third, fourth, fifth. And there's no limit to how many times you can take derivative. You can go forever. All right? And so on. ... That's using Newton's notation. Y'all ready to see it for Leibniz? Leibniz was the other person. This is the notation Leibniz used. For the first derivative, dy dx. Right? That's what I told you earlier, dy dx. Now, after the first derivative, when you get to the second derivative, what we do is we write d with the superscript 2, then the y, then dx, and then superscript the 2 over here. So do y'all see the 2's are offset from each other? The reason why they're offset is because Leibniz didn't want to write this down. He didn't want to put 2's on both, and he didn't want to do this either, because he was afraid if he wrote it this way, you would think you're doing what? Take the derivative and then square it, right? I think you could argue that that would be take the derivative, then square it. Or here you could maybe argue the same thing as this, right? So he said, you know what? The way I'm going to let people know that I'm talking about taking the derivative twice is I'm going to offset the 2's. And that way there's no confusion about something getting squared. And then, of course, the rest just follow the same way. The 3 here, 3 over here. Third derivative, fourth derivative, fifth derivative, sixth, seventh, eighth, ninth, and so on and so forth. Okay? We're almost done with this section. I'm going to go back to last class. In last class, I told you that if you were given a position function, right, where this was time and this was distance, and you had a graph, and you went to some point A, and you found the slope of the tangent line, that the slope of the tangent line would be equal to the instant velocity at x equals a, right? The instantaneous velocity. So if this is time and distance, the slope of the tangent line gives you instantaneous velocity. That's what the derivative does, right? The second derivative is the derivative of the derivative, right? The derivative of the derivative. That's the second derivative. So if this function is f, y'all tell me if y'all understand this or not. What would its derivative be? The derivative, right, this function f, the graph of its derivative is some graph, right? It doesn't have to look the same, sorry. It looks like whatever. This is velocity, right? Which means this is time and this is velocity. So what would the second derivative be? The second derivative, whatever that graph looks like, this would be time and this would be acceleration. That's what this next note says. That if you've got linear displacement, an object moving in a straight line, if the first derivative gives you velocity, that's what this is, then the second derivative, which we will call a of t, will give you the instantaneous acceleration of an object. Now, third derivative we don't worry about in physics as much, well, later maybe, but when you're first learning physics, it's basically position function. The derivative of that will give you velocity function. Derivative of that will give you acceleration function. So if you're in a physics class and they're like, hey, we've got this object moving on, like a spring, and it's moving up and down like a cosine function, and then they say, hey, let's figure out its velocity. What they're going to do is they're going to take the cosine function and find its derivative, and then that would give you the velocity. And then if they want to know the acceleration of that object, they would take the derivative of that derivative, and then they would have your acceleration. So it's a very useful thing for us. We'll get to do some problems with that, but that's the summary right there. S of t is position. The velocity is the derivative of that, which is your how fast it's moving. And then the acceleration is the second derivative, is how fast the speed is changing. All right, we're wrapping this section up. I want to close this. Let's look at this review real quick. So these problems obviously came from this section, right? 2.2? Let's see what other problems came from here. Look at 26 and 27. Oh, mostly number 26. What am I asking for in 26? The second derivative, right? Yeah. That means you have to take the derivative of this, and then after you get that answer, you got to do it again. All right? So we have not done one of these yet, so let's do this. Should I do that one or do a different one? That one. You want that one? Okay, so let me put the function here. F of x equals 3x squared minus 4x plus 5. And for those of you, I know that some of you have seen calculus before, I'm saying here using the limit definition. So I have to use the limit definition to find these, the first and second derivative. All right, here we go. Ready for the first derivative? The first derivative of this function is the limit as h goes to 0 of f of x plus h minus f of x all over h. That's the new definition from today, right? Replacing the a with x. Then this will be the limit as h goes to 0. All right, I first have to plug x plus h into the function, right? It's going to suck. It's going to be 3 times x plus h, that quantity squared, minus 4 times x plus h, and then plus 5. That is just this, right? That's just that right there. And then I need to subtract from that, right? F of x, which is the original function, 3x squared minus 4x. But what do I have to put here, or else I'm going to mess everything up? Parentheses, right? Because we're subtracting the whole thing. That right there, good, is the top right. And then the whole thing divided by h, right? When I'm done with this nasty limit, when I'm done, I should get a new function of x, right? That's what I should get. All right, so now some algebra. Limit h goes to 0. Okay, I need to do this. I need to do x plus h squared, which is x plus h times x plus h and then FOIL, right? Now, if you did your homework, you probably had to do that several times, so you're somewhat familiar with it. So I'm just going to put it here. This is going to be 3 in front of x squared plus 2xh plus h squared. So I'm not showing the work of squaring that. Then minus 4x minus 4h. I'm distributing the negative 4 through. Plus 5. Distributing this minus through. Minus 3x squared. Minus 4x. No, plus. Sorry, messed that up. Minus 5. and then all of this over h, and then distribute the 3, right? Just remember that 3 is going to have to hit everything in here. So I think I'll save myself a little bit of time. 3x squared plus 6xh plus 3h squared. And if I do that, then I don't have to rewrite the whole problem, right? Just distribute that 3. Lots of stuff goes away. Well, is it a lot? 3x squareds. What else? 4x's, 5's, right? All that stuff goes away. So what I'm left with is, let's see, I have a 6xh plus 3h squared. Anything else? Minus 4h. Is that it? Yes. Yes, all over h, right? And the good news is that everything here has an h, right? Everything here has an h, which on the top, sorry, which means I can factor an h out. Pull that h out, I'm left with 6x plus 3h minus 4, and then all over h. Your h's are gone. And at this point, I'm going to let h go to 0. Right? And when I let h go to 0, the only thing that gets impacted is this right here. This goes to 0. And so what am I left with? 6x plus 4. Minus 4. So minus 4. Thank you. Minus 4. Okay. That's it.
And then we would do that again.
Now we got to do it again. But this is our new function, okay? So this right here is f prime of x, right? What we need to do now is do that same limit right here, but we're going to be using this as our function instead, all right? Any questions on any of this algebra? All right.
So the first function we don't have to worry about.
Yeah, now we've got this, and we're going to start the whole process over, all right? Let me see if this makes sense to you. I'm using that formula over there. Does this make sense that if I say the second derivative of the function, this should be the limit as h goes to 0 of the first derivative at x plus h minus the first derivative of the function at x all over h. It's essentially this right here, but I've made that a double prime and then made this prime prime. It's like applying the limit again, but to the derivative, not to the original function, right? So it's like the derivative is going in here, which means this should be the second derivative. Any questions on that? Limit h goes to 0. All right, what is the derivative function with x plus h plugged in? So that's this one, right? 6 parentheses x plus h minus 4. And then minus parentheses 6x minus 4, and then all over h. That's actually going to be a lot easier to work with than the first one was bad, right? The algebra here was, well, not bad, but it was not fun. This one's going to be a little cleaner, I think. Limit h goes to 0. And you've got 6x distribute plus 6h minus 4 minus 6x plus 4 all over h. Good things go away. Good things happen. Things cancel. All I'm left with is limit h goes to 0, 6h over h, and cancel these h's out. And then now you have a constant, right? And the limit of a constant is the constant. Once these h's are gone, you're saying, hey, what happens when h goes to 0? And all you have is a 6 there. So your answer is just 6. And we're done. I'm going to graph these. Just I want to show you. The original graph was 3x squared minus 4x. All right, I'm going to erase all this. What kind of function is that? What does that look like to you? What type of function? Parabola, right? Quadratic function, right? And then let's check.
Oh, it's +5.
Oh, it's plus 5? There we go. All right. That's a parabola, yes? The derivative of that was what? 6x minus 4? Look what I can do on Desmos. See how I typed in f of x equals this? If I just do f prime of x, it'll draw it for me. Like it took the derivative for me. It actually did it for me. If you don't believe me, then I'll have it graph y equals 6x minus 4, and it's the same graph. You see the same graph? And then, let's see how it does with double prime. It just says it, right? Well, there's limitations, okay? It should have graphed that. So what I'm going to do is I'm going to graph it. Was it 6? Yeah, it was 6. So what you see here are the three functions. The original function, the parabola, right? The blue function is the derivative, right? So the red is f prime, or sorry, f, this is f prime, and this is f double prime.
Is it a coincidence that it's 6x minus 4 and 6? Like the 6 is...
There's a reason. We're about to see, actually. What I want you to see here is that the original function was a parabola, right? X squared. Parabola has x squared. The derivative was what? 6x minus 4, which is linear, right? Has x to the first power. And then a constant has x to what power? 0, because there is no x's in there. So we started out with x squared. We took a derivative, we got a linear function which has an x in it, and then we took the derivative again and we have something that doesn't have any x's in it. So it seems like the derivative has this effect of like taking the power of the function down by 1, right? Doesn't it seem like that's what's happening? Is that a coincidence? Is that the way it is? We're about to talk about that. All right, so that was on the review, right? We are done? We found the second derivative? All right, so now what happens in this class is that we say, all right, enough torture, enough of you suffering through limits. Now it's time to give you shortcuts. So now if I want you to take a derivative, you no longer have to use the limit. We're going to give you these formulas so you can just go around the limit and just get the answer, all right? So that is what this 2.3 is about. Actually, the next 3 sections are all about shortcut rules, all right?
Are these on the test?
Only 2.3, all right? We are not going to be able to do this. So let's start with 2.3. So this is just me saying the torture's over. Now we get shortcut rules. You're allowed to use these rules from here on out. You can use these rules unless I tell you to use the limit definition. So on this review, you will see that I say use the limit definition, right? All these problems, use the limit definition. But at the end of the test, or at the end of the review, I ask you to find what? Y prime? Those are derivatives, right? Find the derivative of this, but I don't tell you have to use the limit definition, do I? That means you can use anything, which means I would use shortcuts. So how are we going to address problems like this? Well, let's see. We need the rules, so I need to give them to you first. All right, so here are the rules. Here are the first set of rules. If you ever want to know what the derivative, look at this notation. I want the derivative. I want to treat x like the independent variable, and I want the derivative of a constant. The answer should always be 0. I think you can convince yourself of this if you just think about what this means geometrically. So if I ask you to graph some function, f of x equals a constant. Let me see. How about 5, right? There's a constant. That's a horizontal line, right, through 5? And what is the slope of the tangent line at any point on that graph? What's the slope of the tangent line? 0, right? So the derivative should be 0 all the time. And that's what this is saying. All right? So the derivative of a constant is? The derivative, here's another way I could write it. The derivative of 5 would be 0. Take the constant 5, take its derivative, you get 0. That works for any constant. Is pi a constant? Yes. What's the derivative of pi? 0. All right? Another way you could think about this is remember that the derivative gives you a rate of change, right? If your function is constant, is it changing? No. So what's the rate of change? Nothing, right? No rate of change. 0 rate of change. All right, so the derivative constant is 0. Next one. The derivative of x is 1. The derivative of x is 1. What this means is that if you take the function f of x equals x, do we all remember from college algebra that that's that really nice function that's like a perfect diagonal? Like a